Good afternoon, everyone. I'm Osintsev Kirill, postdoc at Wenzhou University. Today I'll present our research on prediction of the short-range order parameters in iron, nickel, chromium alloys. When high-entropy and medium-entropy alloys were first introduced, they were assumed as random solid solutions. That implied that atoms in these alloys arrange completely at random. However, this picture is wrong. It was found recently that in these complex systems, atoms tend to attract or repulse each other at the atomic distances, and this hidden atomic architecture is called short-range order. And this order extends up to several atomic distances. And this is not just an academic detail. This short-range order can have dramatic consequences. As this graph shows, the strengths can be changed by the presence of short-range order in these complex systems. Short-range order can either increase or decrease strengths by up to 30% in the FCC crystals, as predicted by this theory. And ignoring short-range order means not only being inaccurate, but also can lead to unexpected failure in materials, as well as missing the opportunity to develop more reliable and strong alloys. Our current methods to predict short-range order are density functional theory, cluster expansion, and other sub-methods. They work well. However, they are computationally expensive and are not transferable. That means that for each new calculations with new composition, they require to start from scratch, from the beginning, meaning that fast screening of a vast compositional space is impossible for these methods. The recently proposed non-interacting molecular method by Professor Curtin and Dr. Rao has promise since it is fast and analytical. However, it hasn't yet been used to predict the short-range order in the real systems. This brings us to the question of this work. Can analytical methods, such as the non-interacting molecular method, be used to accurately predict the short-range order parameters in such an important industrial alloy system as iron, nickel, chromium? And to answer this question, we first compared the predicted results with the experimental one. Then we calculated the ternary map for a wide composition space of this alloy system, and then found the hidden rules which connect the composition and the short-range order in this system. How does this method works? The non-interacting molecular method divides the complex system consisted of billions of atoms into small manageable pieces. First, this method calculates the effective pair interaction energies between pairs of atoms in the system. Then these energies are used to predict the probabilities of finding these specific atoms in a specific configuration. So the system is divided by non-interacting configurations, such as pairs presented on the right side of the slide. Then the probabilities of each of these pairs are calculated, and these probabilities then are transformed into the short-range order directly. So this is the comparison of the prediction using by this non-interacting molecular method and the experimental results. We've selected the alloy iron 56, nickel 23, chromium 21, because for this system there have been measured short-range order parameters experimentally. And the method, the non-interacting molecular method, predicted that for iron and nickel pair and iron and chromium pair, the error of the calculation is less than 6%, which is even outperforming the cluster expansion method, which is much more slower. Also, the calculations show that for nickel-chromium pair, it has high ordering. However, the method is underestimating it by 59% of error. However, it means that the method is reliable and can be used to conclude the main tendencies in the system. Then we calculated the ternary maps for each pair of atoms. For short-range order parameters for nickel-chromium pair in the whole composition space has negative value. That means that nickel and chromium tend to order in this system, while iron containing pairs like iron-nickel and iron-chromium has positive short-range order parameter, meaning that they are tending to clusterize. The previous slide showed the big picture, and this slide has a more detailed view how each of the elements influences on the short-range order in these systems. And we found an interesting tendency. The more the iron is added in the system, the more the tendency for nickel and chromium to bring together and order. This is opposite to what we could have predicted and expect for it, because we usually expect that the more the element is added, the more dilution of the property. But addition of iron promotes the ordering of these two elements, nickel and chromium, while adding nickel or chromium separately weaken the strength of ordering for nickel-chromium pair. What is the future research which can be used based on these results? Recent results showed that our traditional assumption that short-range order forms during prolonged annealing is also is not true, because even at high cooling rates, which can be achieved by additive manufacturing methods, short-range order with a similar intensity is formed. And that means that such methods as a nickel non-interacting molecular model is important to predict how the changes in the short-range parameters influence on the mechanical properties of these additively manufactured alloys. And this brings us to the two questions. Because additively manufacturing samples are cooled at different cooling rates, it assumed that there will be non-uniform distribution in short-range order. So such methods as was presented is essential to find the exact values of the short-range order. And also the second question which arises is how much short-range order variations changes the local mechanical properties in the additively manufactured high entropy and medium entropy alloys. So as to conclude, the method provided in this presentation has promised to screen a vast compositional space of high entropy and medium entropy alloys. It allows to accurately predict the weak interactions between iron nickel and iron chromium in iron nickel chromium alloy, and most interestingly, it can show that increasing of iron content in this system has influence on the ordering between nickel and chromium pair. This is just a beginning of my future work, which will be then used as a basement for postdoctoral research in the future. Thank you very much for your attention. I'm ready to answer your questions if you have one.